about ready to get started? Do we have our speakers here?
Yes, I think I have found all of them and already make all of them as a co-host. So probably we can start now. I can start sharing the video.
All right, well, so then welcome very much to session 5C of CAV on model checking. Hope you have enjoyed the morning so far. And our first talk this session is going to be on global guidance for local generalization and model checking. And it's going to be presented by Hari Govind. Hopefully I said that right, Hari, let me know, from University of Waterloo.
Hello everyone, I'm Hari. I'm here to present our work on global guidance for local generalization in model checking. This is joint work with Yuting Chen, Sharon Schwam, and Eric Gurfinkel. So let's get started. We are primarily interested in proving the safety of infinite state systems. Our algorithm works on all systems that can be expressed as nonlinear constraint Horn clauses. However, to keep things simple, we are going to explain everything relative to sequential programs with a single loop. In this context, safety can be established by generating inductive loop invariants. We are particularly interested in IC3 style model checking algorithms. These algorithms generate predecessors to bad states called proof obligations and block them and generalize to learned lemmas. These algorithms do this repeatedly until they generate an inductive invariant. The example on the right is an example sequential program. It has two variables, a and b, both of which are unbounded integers. Inside a while loop that runs arbitrarily many times, both variables are incremented. Once the while loop exits, it is asserted that if a is less than 5, so is b. An example of a proof obligation can be a set of states where a is between 0 and 4 and b is equal to 4. This proof obligation can be blocked using lemmas like a equal to b or a plus b less than 4. So one critical aspect of such IC3 style model checking algorithms is local reasoning. That is, they generalize from single proof obligations. This generalization is typically done using interpolation, and interpolation can be quite magical. For example, interpolation can generate terms like a equal to b even though this term did not appear anywhere in the proof obligation or in the transition system. However, local reasoning has its problems. It is not aware of the structure of the inductive proof constructed so far. Interpolants are a sole function of the heuristics inside the underlying SMT solver. Therefore, as far as an interpolation algorithm is concerned, the lemma a plus b less than 4 is just as good as the lemma a equal to b. However, from a model checking perspective, for this particular program and for this particular property, the lemma a equal to b is better than the lemma a plus b less than 4. However, given a different program or a different property, it could be the case that the lemma a plus b less than 4 is better than the lemma a equal to b. The point here is that it is impossible for the interpolation algorithm to understand which lemma to learn in which context. So this problem is much more crucial in infinite state systems than in finite state systems, because it is very well possible that in an infinite state system, you learn multiple bad lemmas and you diverge. However, in a finite state system, since there are only a finite number of interpolants to choose from, you will eventually converge. So in the paper, we describe 3 different problems with local reasoning. These are myopic generalization, excessive generalization, and getting stuck in a rut. In this talk, we will explain what myopic generalization is. Please read the paper to understand the other 2 problems with local reasoning. Now, there is a nice little comic here. Please read the paper and get back to the slide to understand the comic better. We demonstrate myopic generalization using an example program. This program has 4 variables, a, b, c, and d. All of them are unbounded integers, and all of them are incremented inside a while loop that runs an arbitrary number of times. In each iteration, either both a and b are incremented or c and d are incremented. Finally, it is asserted that if a is less than c, then b is less than d. To see myopic generalization, let's take Spacer, a state-of-the-art IC3 style model checking algorithm, and run it on this example. If you run it in the first iteration, Spacer learns the lemma a minus c less than 0 implies b minus d less than 0. This is in fact the property that we want to prove. However, Spacer has not proven that this is inductive, therefore we continue. In the next iteration, Spacer learns 2 lemmas, a minus c less than 1 implies b minus d less than 1, and the same lemma but with a constant minus 1. What is going on here? Well, Spacer actually splits on the if then else branch. To learn one lemma, it follows the then branch. To learn the other lemma, it follows the else branch. Okay, now as Spacer progresses, it learns more and more lemmas which are very similar to the previous lemmas that it learned. We all see where this is going. Each of these lemmas are good enough to block single proof obligations, but none of them are good enough to learn to be an inductive invariant. So even though Spacer learns many similar lemmas, Spacer does not figure out that it's not making progress. This is what we mean when we say that local reasoning is myopic. So how do we solve this problem? Well, we introduce global guidance. Okay. So this is Spacer. It has 2 main data structures, a proof obligation queue and a lemma trace. In each iteration, Spacer queries a proof obligation queue for a proof obligation alpha. It queries a lemma trace for a frame OI. It tries to block alpha. If it's not successful, it generates a new proof obligation, alpha dash, and if it is successful in blocking alpha, it learns a new lemma L. This is where global guidance kicks in. When Spacer is about to learn a new lemma, we take a global view of the proof by querying a subset curly L of lemmas from some frame OK and taking a proof obligation phi, and then we guide Spacer by learning a new lemma psi and adding it to the lemma trace, or generating a new proof obligation gamma and adding it to the proof obligation q. We introduce three rules: subsume, concretize, and conjecture to achieve global guidance. In the rest of the talk, I'll explain these 3 rules. The first rule is the subsume rule. It says that if you have a bunch of lemmas curly L such that you can generate a new lemma psi that subsumes each of the lemmas in your subset, then you can add psi to the trace. Just to get an idea, imagine that Spacer learns 2 green lemmas in some context, and after a few iterations, Spacer learns 2 more green lemmas. Now, what's Spacer trying to do here? Spacer is trying to represent a set of an over approximation of reachable states using a set of lemmas. If we apply the subsume rule, we can represent the same set of the same set of over approximation of reachable states using a single lemma psi. What is the advantage of learning a single lemma? Well, it can be it is much easier to generalize the single lemma than to learn infinitely more green lemmas. To make things more concrete, I will explain the subsume rule on the running example we had. Recall that earlier Spacer diverged by learning lemmas of the form a minus c less than 1 implies b minus d less than 1, and with different constants instead of 1. In order to compute a subsume lemma, we first go into the cube space, which is the negation of lemma. Now we can see that each of these are now conjunctions rather than implications. The nice thing about this is that these are polytopes. We can apply a convex closure algorithm to compute the convex closure of these three shapes. In fact, we can make certain assumptions so that computation of convex closure is simplified. Please read the paper for the assumptions that we make and the new algorithm that we get for computing convex closure. So let's say we do compute the convex closure. It is going to be this red region. It has three literals. First is the nice literal a minus c less than b minus d, and the other two literals are boundary conditions. These two boundary conditions can be dropped by using inductive generalization. Now, if we transform this cube into a lemma by taking its negation, we can see that we can actually get an inductive invariant for our running sample. Okay, so that's all about the subsume rule. Now I'm going to explain the second rule, which is concretize. I'm not going to explain the formula here. I'm just going to explain it pictorially. Imagine that you have a proof obligation, which is a yellow circle, and it's difficult to block that using a single lemma. In this case, we can use concretize rule to divide and conquer this proof obligation. On application of the concretize rule, you get an under approximation gamma of the yellow region, and you can ask spacer to block this under approximation. Once spacer blocks this under approximation, it will learn a new lemma, which is the blue zone here. This new lemma will definitely block the under approximation, but it need not block the original proof obligation that we started off with. So we can apply the concretize rule again to divide the proof obligation again and block it to learn a new lemma. The hope here is that when we do it enough times, we can generate a number of lemmas which can be put together and generalized to block the whole proof obligation. In the paper, we explain in detail what exactly we mean by terms like partially blocks and how to under approximate a proof obligation for the theory of linear integer arithmetic. Please read the paper for such details. Now, the third and the final rule for global guidance is the conjecture rule. It is applicable when the proof obligation 5 has two regions, the violet alpha region and the yellow beta region. And there are a bunch of lemmas, bunch of green lemmas that block only one part of the proof obligation. In this case, all these lemmas block the yellow beta part of the proof obligation, but none of them block the violet alpha part. So the conjecture rule allows spacer to abstract this proof obligation to get an over approximation, which is the alpha region. Now, if we add alpha to the proof obligation Q and block it and generalize, maybe we'll get a nice blue region, which might be an inductive invariant. Again, we go into much more detail about when the conjecture rule is applicable and how to construct the alpha region from the proof obligation. Please read the paper for those details. Okay, so far we have seen global guidance. Global guidance is achieved using three rules: the subsume rule, which adds a new lemma psi to the lemma trace; the conjecture rule and the concretize rule, which generate a new proof obligation gamma and adds it to the proof obligation Q. There is the conjecture and the concretize rules are complements of each other in the sense that conjecture rule over approximates a proof obligation, whereas the concretize rule under approximates it. Okay, so we implement these three rules on top of spacer, and we call the new solver gspacer. We evaluate gspacer on linear integer arithmetic instances from the CHC computation, and we can see that in fact gspacer solves almost 20% more instances than spacer. But more interestingly, gspacer is stable even without interpolation. That is, Even if we turn off interpolation, GSpacer does not lose performance. Whereas in the case of spacer, turning off interpolation leads to a decrease in performance. GSpacer also participated in the latest edition of the CHC competition, and it won 3 of the 4 tracks. The second part of our evaluation compares GSpacer with linear arbitrary. This is a data-driven, machine learning-based invariant inference algorithm presented at PLDI 18. And it stood out because its evaluation showed that it outperformed spacer on a curated subset of benchmark instances from SVComp. We tried to compare a GSpacer with linear arbitrary, but could not compare it on the CHC competition instances because linear arbitrary was pretty poor. In fact, it was much poorer than spacer on those instances. So we compared linear arbitrary with GSpacer on the benchmark instances from the PLDI 18 paper. We first replicate their results. That is, we can see that spacer solves much fewer instances than linear arbitrary. However, we find that GSpacer solves more instances than linear arbitrary. So to conclude, we present a global guidance technique to mitigate limitations of local reasoning. We find that the global guidance technique is stable under different interpolation strategies. In fact, it is stable even if interpolation is turned off. Finally, we conclude that adding global guidance to model checking algorithms is very effective. In fact, it is more effective than invariant inference algorithms like linear arbitrary and local reasoning based model checking algorithms like spacer. As future work, we would like to extend global guidance to other theories, especially theories where there is no interpolation, like bit vectors or arrays. We would also like to add more rules. Specifically, we believe that global guidance can help symmetry breaking while verifying distributed protocols. Thank you for listening.
Thank you very much, Hari. I know everyone's on mute, but for those of you with cameras, I've been told jazz hands is the appropriate way to applaud here. We have a couple of questions that were posted by Aman Gol on the Slack channel. So please post any additional questions there. I'll read the questions out loud for you. Aman writes, looks like equality predicates like A equals B are sufficient to find the quote unquote better global lemma instead of a local lemma with A minus C less than 1. Are there other examples without equality predicates where global guidance can help? And also, do you have any comments on how many additional SMT or stat query, how much additional overhead is introduced, if any, compared to spacer due to global guidance? And Arya's been posting some replies, but Hari, I didn't know if you also wanted to maybe address these questions, expand on the response.
So unfortunately, Hari can't answer because his internet went down just when the talk started. So I've been trying to get in touch with him. I know he's fine. He just can't connect with full bandwidth. So I'll answer the question. So first is equality. It's a good observation. In fact, in many simple examples we tried, equality is really important. But we find all kind of convex closure dependencies. The equality is just the most common example and the easiest one. And in fact, we have a special module that tries to first find all equalities and then simplify the problem so that we only compute the real convex closure after equality has been done. Now, the second question about the overhead, that's really hard to measure because as soon as we change lemmas that we learn, we also change how the solver behaves. And so if you learned one different lemma early on, the rest of the solver is very different. And so we compare the total time, but it's very hard to say like what is the overhead that we introduce with extra SMT queries. That's it.
We have a new question. Oh, I'm afraid I'm not going to pronounce your name correctly. Amir. Okay, and now it scrolled off the screen. Nazari. And the question is, what level of soundness and completeness can you obtain by concretizing? And how many false positives and false negatives do you see with this approach? And the question is asked because of the under approximation element of the algorithm.
Great. So this is maybe a misunderstanding. There are no false positives or false negatives. There is an under approximation, but this is the typical under approximation in IC3, that the predecessor states of proof obligation that you compute are under approximations, and what you learn is an over approximation. So when we concretize, what we say is that even so we know that a bed region is that big, maybe it's more effective to try and take a small chunk of this bed region, prove that that chunk is unreachable, and then generalize that into a bigger chunk. Okay? So it seems counterintuitive. Why would you want to take a smaller region and prove things when you know that a bigger one has to be blocked? But once you look at the signature of the relations involved, the formulas that you write, sometimes something is a bigger region requires more complicated logic to describe. In our particular case, we're looking for things that seem to converge to nonlinear expressions, like a circle. And then we would say, well, we're never going to generalize into a circle anyways, because we only do linear arithmetic. So let's try and concretize and drop some of the things that look quadratic, and maybe we'll get a different proof that doesn't depend on them. Should I read the questions? I see them as well.
Oh, it's fine. I can read them. I was going to say we have two more quick questions. So Oded Padan asks, do the three rules somehow consider the transition relation, or are they purely about states and formulas? And can you comment on the relation to beautiful interpolants? And he gives the citation for the CAV 2013 paper with that name.
So the rules don't really consider the transition relation. We really look at the proof obligation that appears or the lemmas that are learned, and we try to cluster them together and then say, oh, looks like we're learning lots of lemmas of this kind, and maybe there's a better lemma that captures the same thing. So we're only looking at the lemmas that are learned. It's almost completely true. We need to make sometimes some heuristic choices by picking, say, when we under approximate, to pick some numbers. And for that, we do go into the transition relation and we mine the numbers from there. And so whenever we have to make basically a non-deterministic decision, sometimes we'll say, oh, let's pick the closest number from the transition relation that works. But we don't do much more from the transition relation than scrubbing it for actual numeric constants that appear. Now, relation with beautiful interpolants, it's harder. There's some similarity because we also look at convex closure. But everything else is different. Like the algorithms that we use to compute the convex closure are different. When we choose to do it, we don't go from individual points. We're going from symbolic proof obligations. It's really hard to summarize like what is the key difference between the two. They're just very, very different.
Okay. Yeah, and you've got a few follow-on questions for that, like, for example, better interpolance techniques from selfless interpolation for infinite state model checking. So I'll let you guys address those offline. It looks like Hari's back online too, so welcome back. Sorry your internet went down at an inopportune moment. And thank you very much for a great talk. I loved the graphics and the cartoon that so nicely displayed the different elements of the techniques in a space context. Where did the name of the tool come from?
GSpacer for global spacer?
Well, I mean spacer originally.
Oh, the spacer originally. We've just been doing the space theme and that just came out. I used to have a tool before that with Aus called the UFO. And so we had to have some space theme and spacer came.
Okay. Well, thank you very much, Ari and Hari. Our next talk is going to be toward model checking real world software defined networks, and it will be presented by Vas Klimas.
Hello everyone, my name is Vasilis and I am PhD student at University of Sussex. This work proposes MOX, an optimized and highly expressive software-defined network abstraction that allows capturing subtle real-world bugs. I will start this talk off by briefly summarizing the problem. Software-defined networking brings the benefits of network-wide visibility, control, and order to managing network complexity. At the same time, however, new verification challenges are introduced. Software-defined networks are asynchronous, distributed systems with complex software stack. Decoupling traditional networking into dynamic components and layers that have to work in unison adds greater performance vulnerabilities to the most basic network functions. Further, the softwareization of network functions and open sourcing it do not come without cost. Third-party applications are a very common source of bugs. Open sourcing would mean having to refactor the code, which may make the source code more susceptible to have latent bugs. Malicious users also can potentially exploit vulnerabilities. Traditionally, debugging networks has been an art rather than a science, relying heavily on unsystematic and reactive procedures, and we will fix it when it breaks operational attitude. The most common network debugging and troubleshooting tools in legacy networks are ping, traceroute, TCP dump, SNMP statistics, etc. Despite the progress made in developing and applying sophisticated formal methods frameworks, networks in general, and SDNs in particular, have largely resisted analysis using formal techniques. The main reason for this is that the issue of scalability still remains the Achilles heel in this domain. Networks are hard to verify due to the huge amount of state. Packets can show up anytime, from anywhere. There is a large number of events due to the highly dynamic network state changes, resulting in a high number of interleaved orderings. So, there is a huge state space that we need to deal with. In order to enable the verification of network-wide properties in larger real-world software-defined networks using fewer resources, we present an extended network model called MOX to capture more realistic complex interaction between the software-defined network controller and the data plane. First, MOX is more general than prior models in the sense that it is closer to the OpenFlow standard, and as such, it reflects commonly exhibited behavior between the controller and the network switches. Such extensions include allowing race conditions between controller messages and introducing barrier response messages. Another contribution of our work are the context-dependent model checking based patch order reductions, by considering the concrete control program, the network topology, and the specification in question. These optimizations are crucial for tackling the state explosion and scaling up. For all the proposed optimizations, we establish their soundness. Moreover, in order to further improve performance, we propose state representation optimizations, namely packet and rule indexing, identification of packet equivalence classes, and bit packing. Our model has been inspired by another work on model checking software-defined networks, named QI. According to the contributions above, however, we consider MOX to be a considerable improvement. We model more OpenFlow messages and interactions, enabling us to check for bugs that other approaches cannot even express. Our context-dependent patch order reductions systematically explore possibilities for optimization. And overall, our optimization techniques still allow MOX to run at least as efficiently as other frameworks, often with even better performance. The direction that we follow here is that of model checking, aiming at providing exhaustive and automatic debugging or verification. As modeling mechanism for concurrency, we consider communication based on shared state through interleavings. Concurrent threads interact through reading mutating shared data queues as shown in the slide. For example, if a packet is sent from a host to a switch in the left-hand side picture, if there is no matching rule in the flow table of the switch, then the switch will ask the controller how this packet should be handled. by adding the packet to the request queue of the controller. Next, the controller sends back instructions on how this packet should be treated, and a set of rules is sent as well in order to match further packets of same shape. On the right-hand side are shown the shared queues of the system, the valuation of which constitute the state of the system. More formally, the states of a software-defined network transition system are tuples pi, delta, gamma, where pi represents the state of each host, which is a mapping from host to receive queues, delta, the state of each switch queues, and gamma, the controller state. The control plane substate gamma consists of a local control program state CS and an assignment to control queues request queue, RQ, and barrier reply queue, BRQ. The controller program, which is used to parameterize the SDN model, consists of a set CS of local program states and two event handlers, packet in and barrier in. Incoming packeting and barrier response messages from the SDN model are stored in RQ and BRQ respectively, triggering the controller corresponding handlers packet in and barrier in, which in turn respond by potentially changing the program state and sending messages to a subset of switches. To represent the behavior of an SDN to be checked, we model it as a state machine and use Kripke structure formalism as an abstract model. As you may already know, a Kripke model is a relational model, can be roughly pictured as a graph with labeled edges and nodes. There are some nodes referred to as possible worlds or states or situations, with some relations among them labeled by some symbols, which are the actions in our case. And each node is labeled with a set of atomic proposition letters. We parameterize the model by the underlying network topology lambda and the controller program CP in use. Transitions are protected by Boolean guards, which are enabling conditions. A guard is a predicate specified over the state at which the action is taken. So a state is the evaluation of all the variables in the system, and transitions are happening due to the events that change the value of the variables. Now, the big picture here illustrates a high-level view of open flow interactions, left side, and the modeled actions and queues, right side. Actions here encode the events the network may engage. The concurrent threads interact through dequeuing and enqueuing shared data queues, as shown in the figure. For example, when an action fires, it dequeues an item from the buffer the arrow begins at, or decrements the multiplicity of the item if the buffer is a multiset, like the packet queue, for example, and possibly adds an item in the queue the arrowhead points to, or multiple items if the arrow is double-headed. In order to specify properties of packet flow in the network, we use linear time-temporal logic formulas without next-step operator. The reason that next step is not included is that stutter equivalence does not preserve the truth value of formulas with next. An atomic state condition can assert about the existence of a packet located in a packet queue of a switch or in a receive queue of a host that satisfies the specification property P. The atoms can also assert about the controller in a specific controller state queue. In order to be able to express that a condition holds when a certain event happened, which cannot be read off directly from the state valuation, we extend the LTL state-based logics with action-based dynamic logics. For example, the property that a packet destined to server with IP1 should never be dropped can be expressed in dynamic logic by the dual modal construct shown in the bottom of this slide. We mentioned that scalability is an issue in model checking. Prior works on SDN verification via model checking attempt to get around the scalability barrier by maneuvering the model, for example using logs, in order to hardwire orderings and synchronize threads. which of course causes loss of observable behaviors, sacrificing this way expressiveness for efficiency. In order to cope with the explosion, we employ patch holder reduction, which exploits the independence between concurrent actions to avoid redundant explorations. For example, given two independent actions, the combined execution of which has the same effect, exploring both threads is meaningless. We omit one, keeping just one representative from the equivalence class of threads. We extend this notion by considering conditional independence constraints. Two actions might be independent and invisible only in the particular context explored, which means they do not write on a shared variable and do not affect state labeling. Now, context for us is the triple network topology lambda, the controller program CP, and the property phi at stake. The ultimate aim, of course, is to find more safe actions which do not need to be interleaved with other threads. So, the more actions that are both stutter and provably independent, also referred to as safe actions, the smaller the transition system and the more efficient the model checking. And this constitutes the main contribution of our work, attempting to identify as many safe actions as possible to make patch holder reductions more widely applicable to our model. Computing potential patch holder reduction scenarios requires some additional guard checks at runtime. This technique is generally applicable as shown in the evaluation section later. A patch holder reduction that is unaware of context makes the observation that there is typically a large amount of redundancy in the state graph that stems from the commutativity in the execution of the transition system. The context-aware patch holder reduction that we apply here, on the other hand, is weaker than the context-insensitive one. It observes that there is an even larger amount of redundancy. This happens when executing transitions which are contextually independent and when the property cannot be distinguished between the permutations of these independent executions. So, rather than exploring through all enabled actions in the current state, only a subset of these actions, the so-called ample set, is used to generate the successes. The ample set in a state consists of all the independent and invisible actions, also called safe actions, enabled in this state in the context at hand. If there are no safe actions enabled in the state, then the ample set consists of all the enabled actions. To give an insight to how an action might be safe only in particular contexts, consider the network in this figure. Suppose packet P, whose destination TCP port is SSH, is added by the controller in the forward queue of the switch along with a forwarding port 1. The pair packet P port 1 enables a forward action. This forward action is an unsafe action in the context 1 because it is observable for the property phi 1. It is, however, safe in context 2. In the paper, you can find the safeness predicates for 5 action sets of our model. In order to minimize MOC's memory footprint and enabling it to scale up to relatively large network setups, only one single instance of packet and rule that can appear in the modeled network is kept in memory. An index is then used to associate queues and flow tables with packets and rules, with a single bit indicating the presence or absence. This data structure is illustrated in this figure. A value of 1, for example, in the flow table section of the rule indicates that the rule is installed in the flow table of switch 2. Another optimization that we propose in this work is the discovery of equivalence classes of packets that are used for model checking. After removing all the fields that are not referenced in a statement or rule creation or deletion in the controller program, we identified packet classes that would result in the same controller behavior and generate one representative packet for each class. Then, we assign this packet to the network switches that are directly connected to end hosts, modeling this way clients that can send an arbitrarily large number of packets in a non-deterministic fashion. Bit packing is another state representation optimization. We reduce the size of each recorded state by employing bit packing using the 32-bit integer type supported by UPAL. We then perform bitwise operations for the entries in the packet and rule indices, as well as for the packets and rule themselves. We measure MOX performance using three examples of network controllers: a stateless firewall, a stateful one, and a Mach learning application. We investigate the behavior of MOX as we scale up the network by increasing the number of switches and client servers. In this slide, we report the verification throughput in visited states per second. In order to assess how MOX different optimizations affect its performance, we report results for system variants with and without patch roller reduction and state representation optimizations. We also compare MOX against QI, which is a work we build on and extend it. MOX performs significantly better for all different network setups and sizes, achieving at least double the throughput QI does. Also, the computational overhead induced by our proposed patch roller reductions is minimal. In this figure, we present the state space for the various setups and network deployments that we mentioned earlier. We stopped scaling up the network deployment for each setup when the verification process required more than 24 hours or started swapping memory to disk. For these cases, we kill the process and report the top-up bar. It is obvious that the proposed patch roller reductions and identification of packet equivalence classes minimize considerably the number of visited states. This figure shows the memory required by model checking for the same three benchmarks used as before. Obviously, the main factors that affect the memory footprint is the packet and rule indexing and bit packing. Well, that's it. I'm afraid that's all we've got time for this talk. I hope you are still awake and you got something out of it. Thank you.
Thank you very much, Vasilios. Jazz hands.
Hello, hello, hello.
Hi, we can hear you. Yes?
Cool.
So we have a couple questions for you. The first one is from Labna Guda. Are you able to visualize the path between the source switch and destination switch? And what if there are multiple equivalent paths between them?
If I understood correctly, whether we are able to explore reachability or proper reachability properties, I didn't get the question correct.
If you're able to visualize the path, but my interpretation sounds like
of course, because yeah. So model checking is about if there is a bug found, then the counter example is returned, so all the trace is visible to us, telling us exactly that all the states through over the model checking has explored. Of course, yes.
Including if there are multiple equivalent paths.
Multiple equivalent, but what does it mean? Equivalent in terms of what? Of labeling, of state labeling? It depends. Of equivalent paths, we are trying to reduce all the redundant paths, so we keep only one representative class for all the explorations. So there are no equivalent class, but I don't know what exactly my friend is asking, whether it is in terms of state labeling or edge labelings or whatever. We can discuss it if he needs more details. We can discuss offline. He can mail me. Yes. Yeah.
So the next question is from Amir Mohammed Nazari. And is it possible to verify properties in all layers of a network via your approach, or can you only use it for a specific layer of a network?
Look, software-defined networks simplifies we don't have now 7 layers as in traditional IP networks. We have just the data plane layer and the control plane. So we are working in this. This is about SDN. So we are verifying properties in data plane as well as we are verifying properties on controller program. So, which this one implicitly include all the 7 layers of the traditional network, yes, because all the network protocols of the traditional networks now are programmed into the control, in the control plane level. So it's a control program that all the network functionalities are implemented in the control plane. So yes, in this sense, we cover all 7 layers of the traditional IP network.
And then I actually had one more quick question before we go to the next talk.
Okay.
So when you were talking about detecting and then reducing by equivalence classes, I was just wondering how many packet equivalence classes did you end up with?
This depends on the abstraction. It depends on the controller program, how many packets we are required to launch to the network. Now, the equivalence classes are defined purely by the controller program, how many packet match fields we are required to prove the correctness of the property. And the topology depends on the topology. So it's purely contextual. So it depends on the topology, on the controller program, on the match fields that we are required that are engaged in our. So it depends, it's contextual. If you have one property, a phi 1, for example, and a network topology lambda 1, you might end up with X, for example, equivalence classes. But under another property and other match fields and topology, you might end up with different number of equivalence classes.
Yeah, mostly I was just wondering a ballpark. Like, do you see a significant reduction to a very small number of classes, or are there a very large number of classes with only a few things in each?
Yeah, it depends on whether in sense of when we are executing verifying properties, we manage to identify some equivalence classes, but when we are trying to run the model checker as a debugger, then we explore much more state space, so we identify less and less equivalence classes that represents the whole state space.
Okay.
So there is the difference between verifying the correctness and when the model checker is running as a debugger. It's quite different.
Yeah, yeah. One more quick question that just came up. In this context, is topology static or dynamic?
The topology is static. Everything is static, and the pre-computation of the equivalence classes and the guards and evaluation of that is static. Everything is static. Dynamic is something that we have in our mind for some future work, but yeah.
Awesome. All right. Well, thank you very much again. My jazz here.
Any questions, I'm happy to answer either in offline or email. Happy to answer, yeah.
Yeah, the Slack channel seems quite active. So,
Yeah.
so you can
Good.
jump onto that. And with that, we will move on to the next talk. So Stephen Siegel from the University of Delaware will be presenting on action-based model checking, logic, automata, and reduction.
Hello, I'm Steve Siegel, and this is action-based model checking, logic, automata, and reduction, joint work with Yihao Yan. An execution of a concurrent system is often modeled as a sequence of states and transitions. To specify such a system, one can focus either on the states or on the actions, that is, the events that take you from one state to another. Both approaches are useful, and one may be more appropriate in a certain context than the other. State-based model checking is probably more familiar here at CAV, but action-based formalisms are also widely used and important. Process algebras and the closely related concept of labeled transition system use an action-based model of concurrency. So does the literature on assumed guarantee reasoning. There are several state-of-the-art model checkers that use an action-based approach, and these have numerous significant industrial applications. In this paper, we look at some of the most important results from state-based model checking and ask what their analogs are for actions. Some of them are well known, but we found some gaps that we've tried to fill in. Starting on the state side, we typically start with a set of atomic propositions, AP, and a labeling function, L, which assigns a set of propositions to each state. An execution is then represented as a trace consisting of an infinite sequence of sets of atomic propositions. A property can be specified in different ways, but two of the most popular ways are as LTL formulas or Buchi automata. The notion of stutter invariant language plays a very important role in this theory, both because it seems to be a natural restriction on the language for expressing properties, and also because it enables one of the most important optimizations of model checking, namely partial order reduction. Importantly, there are decision procedures for determining whether a LTL formula or Buchi automaton is stutter invariant. And there's a normal form for any stutter invariant Buchi automaton that can be used in an on-the-fly partial order reduction algorithm, which provides a very significant optimization on the standard model checking algorithm. On the action side, we typically start with a set of actions and a subset of those which are considered to be divisible actions. An execution is represented simply as a sequence of actions. Properties can be specified again in many different ways, but LTL and Buchi automata are two of the ways that have been commonly used. The analog to a stutter invariant language is what we call an interruptible language, which we'll define shortly. We'll also show that there are decision procedures to determine whether an LTL formula or BA is interruptible. And we'll show that there's a normal form for interruptible BAs, which is different from the normal form in the state-based case, but which plays the same role in partial order reduction. Given a set of symbols ACT, we can define the set of LTL formulas over ACT in the usual way. Those formulas can be given both a state semantics and an action semantics. The state semantics are interpreted over infinite sequences of subsets of ACT. For example, such a sequence zeta satisfies in the state semantics a formula A if A is an element of zeta evaluated at time 0. Just one small change is needed to define the action semantics. Now zeta is an infinite sequence of actions, and zeta satisfies A if and only if A equals zeta of 0. That's the only change. We can also define two notions of equivalence for LTL formulas. Two formulas F and G are state equivalent if they're satisfied by the same infinite sequences of subsets of ACT. F and G are action equivalent if they're satisfied under the action semantics by the same infinite sequences of ACT. Now, state equivalence is decidable. This is well known. It's equivalent to saying that the validity problem is decidable for LTL. State equivalence is stronger than action equivalence. It's not hard to see. In fact, it's strictly stronger because a formula like A and B is certainly not state equivalent to false, but it is action equivalent to false because you cannot have two actions occurring at the same time under the action semantics. Action equivalence is also decidable. Here's why. Given two formulas F and G, let A be the set of all actions that occur in F or G. Then you can form this formula, this LTL formula H, which basically says that at every time step, at most one of the actions in A is true. And then it can be shown that F and G are action equivalent if and only if F and H is state equivalent to G and H. Since state equivalence is decidable, we now have a decision procedure for action equivalence. Just as in the state case, an LTL formula can be converted to a BA with alphabet ACT in the same action-based language of the formula. I'll just illustrate how that can be done on an example. Starting with this LTL formula, that can be converted into a state-based BA, here we're using the spot library, to generate the BA that you see on the left. Now, to form the action-based BA, I'm going to keep the same states, but change the edges. For every edge in every action, for example, for this edge in action B, set B to true and all other actions to false, evaluate the corresponding formula. If it evaluates to true, as it does in that case, then I have an edge over here labeled B. Do that for all edges and all actions, and you have the resulting BA on the right. Here, tau represents any action in act, but not in A, B, or C. Let's review stutter invariance. A stutter occurs in a state execution when a state label is repeated. Two executions are stutter equivalent if they differ only by insertion or deletion of stutters. And as I said before, there's an argument that real properties should not differentiate between stutter equivalent executions, and also stutter invariant properties are amenable to partial order reduction. Now, given an LTL formula F, can you determine whether it represents a stutter invariant language? The answer is yes. There's a famous result which says F has a stutter invariant language if and only if it's equivalent to a formula without the next state operator. But I should point out that it's actually an active research area to design efficient algorithms for checking that property. The same situation holds for BAs. There are decision procedures which can determine whether a given BA represents a stutter invariant language. What is the analog of stutter invariance for actions? If I have a stutter at step I in an execution, that means that label of state Si-1 is the same as the label of state I, then action AI did not change the truth value of any atomic proposition at that step. We call such an action invisible. Hence, stutters in the state sequence correspond to invisible actions in the action sequence. Note, they do not correspond to stutters in the action sequence. A stutter invariant state property, when expressed as an action property, satisfies that the property is invariant under the insertion or deletion of invisible actions. We call these interruptible properties, and we're grateful to Mark Jasper for inventing that name and letting us use it. These are not new observations. Valmari made them over 2 decades ago and referred to this as action stutter. To make this precise, suppose we're given a language L, which is a set of infinite sequences of actions, and a set of visible actions, V. We define this symbol, zeta, restricted to V, to be the projection of zeta onto V. That's just the result of removing all the invisible actions. We say that two such sequences are equivalent if their projection onto V is the same. And we say the language L is V interruptible if for any equivalent zeta and eta, one of them is in the language, if and only if the other is. We say an LTL formula F is interruptible if its action-based language is V interruptible, where V is just the set of all the actions that occur syntactically in the formula. Almost any action-based temporal property that you encounter in the wild is going to be interruptible. We give lots of examples in the paper. Here are some. Let's consider, for example, this one. For any n greater than or equal to 0, there is a property that says A occurs at least n times. That's interruptible, because if you insert or remove some B's or any action other than A, it cannot affect the number of times that A occurs. The case n equals 2 is interesting. That's expressed by this LTL formula, eventually A and in the next state, eventually A. Notice that formula is not stutter invariant. These are two distinct classes of formulas, the stutter invariant formulas and the interruptible formulas. There are non-interruptible properties. For example, the formula A or henceforth A. Both are satisfied by the word, which is an infinite sequence of A's, but they're not satisfied if you insert a B at the beginning of that sequence. You could argue these are not very realistic properties. In the paper, we describe an algorithm to decide whether any LTL formula is interruptible. The basic idea is that we define a certain transformation on formulas called beta. And we show that given any LTL formula F, beta of F is interruptible. And furthermore, F is interruptible if and only if beta of F is action equivalent to F. Since we've already seen that action equivalence is decidable, we have a decision procedure for interruptibility. We also define a certain normal form for Buchi automata. Let B be a BA with alphabet A and V a set of visible actions. Then we say B is in V interrupt normal form if it satisfies a few simple structural conditions. For example, this condition says that if there is an invisible transition in B followed by a visible transition labeled A, then B must contain a transition from the first state directly to the third state with the label A. We show that if B is in V interrupt normal form, then the language of B is V interruptible. And we also define a transformation on Buchi automata, norm BV, which takes any Buchi automaton B and returns one in V interrupt normal form. This is the Buchi automaton we looked at before. Recall that tau represents any invisible action. It's not normal. For example, I can go from 0 to 2 on tau and then take A to stay at 2, but there is no transition from 0 to 2 labeled A, and therefore it does not satisfy one of those conditions and it's not normal. The normalization procedure would transform the BA on the left in a series of stages to the one that you see on the right. This one is normal, and it turns out it has the same language as the one on the left. Finally, we prove this theorem. For any Buchi automaton B, the language of B is V interruptible if and only if B and the norm of B, comma V are equivalent. That is, they have the same language. And since there are algorithms for determining whether two Buchi automata have the same language, we have a decision procedure for interruptibility of Buchi automata. Finally, we describe an on-the-fly model checking algorithm for interruptible properties. The algorithm accepts a concurrent system specified as a parallel composition of labeled transition systems and a Buchi automaton representing the negation of the property you want to check. The states of the synchronous product are enumerated explicitly. Nested depth first search is used to detect accepting cycles, and an ample set style on-the-fly POR algorithm is used to restrict the search to certain subset of the enabled actions at each state. Is this algorithm sound? Yes, as long as B is an interrupt normal form, and we have an example in the paper that shows that assumption is necessary. This result is similar to a recent result in the state-based case. All of the algorithms I've described, we've implemented in a new model checking tool called McRERS. We've applied McRERS to a large suite of concurrent systems and LTL formulas from the annual RERS challenge. We have used McRERS to check the interruptibility of all 940 LTL formulas from that challenge, and the result is that almost all of them are interruptible, the non-interruptible ones occurring in 2 of the years, and this agreed exactly with the expectations of the organizers who generated that suite. We also used McRERS to convert all of the interruptible formulas to BAs, check if they're in normal form, normalize the ones that are not in normal form. Again, all but 10 were already in normal form, and the total runtime for all of that was 17 seconds. So at least for examples of the size in this suite, performance does not seem to be a problem. We also used McRERS to model check all the problems from 2019. There are 9 different concurrent systems, each with 20 LTL formulas, some of which hold and some of which don't. So first, McRERS got all of the correct answers for all 180 problems. That's good. This table shows you the time to do each problem, In the largest problem, for example, which has 70 different components in the concurrent system, it took McGruer's only 432 seconds to solve all 20 LTL formulas. So that's very fast. This gives you an example of how dramatic the savings is from partial order reduction on this one model checking task from problem 106. Using partial order reduction, the model checking completes in less than 1/10 of a second. With the partial order reduction turned off, that time goes up to over 7,000 seconds. The number of states, transitions, and memory also blow up similarly. Okay, there are many more details and discussion of related work in the paper, but since I'm out of time, I'll stop here and take questions. Thank you.
Thank you so much, Stephen. I actually had a couple of related questions. When you were talking about converting the LTL to the action BAs, you were constructing explicit Buki automata using the SPOT algorithm, which to my knowledge is the state of the art, the single best algorithm for creating explicit BAs from Bushi automata. But I was wondering if you had considered or were planning to consider as future work also conversions into symbolic BAs, because that's a little more murky. I had a paper, for example, back in FM11, where we looked at 30 different ways of representing LTL formulas as symbolic Bushi automata, and they had very different performance in terms of satisfiability and in terms of model checking. So I was wondering if you might look into that and how that would manifest in the term as it relates to action BAs. And then also that would, of course, mean that you could use different model checking methods as a backend. And so, and of course, partial order reduction would not apply the same way. But I was wondering about looking into those aspects of this problem. It's very interesting work.
What's a symbolic BA?
So instead of explicitly representing individual states and transitions, you represent them with logical formulas as sets of states and sets of transitions. So generally it's any method, and there are many. That's why we had, for example, 30 in my FM11 paper, and that's not a limit. There are, of course, many more. That was how many I came up with. But any way of representing the full information space, but as sets of states and sets of transitions, so that you can reason over it more efficiently using logical formulas, at least in part, instead of explicit individual states and individual transitions.
Yeah, I see what you mean. No, I haven't looked into that, but I'm almost certain that would be possible, and it shouldn't be too difficult because the states don't change in the BA when you're translating it to an action BA. And the edges, you're just sort of restricting them, you see. Instead of, you know, in the state BA, you're going to have edges labeled by any set, any set of atomic propositions. And all you want to do is filter out the ones that, filter out those sets that are not singleton sets. So I'm sure as long as it's encoded in any reasonable form as formulas, et cetera, that there's a way to do this transformation within that form, I would guess.
Okay, yeah, I would be really interested in seeing those results, or even collaborating with you if you're interested on looking at ways to do that, of having like symbolic action BAs and different methods of reasoning over those symbolically. We have another question on the Slack channel. So this is also from Amir Mohammed Nazari. Hopefully I'm getting better at your name. And that says, is the interruptibility algorithm that you mentioned both sound and complete?
Yes, absolutely, because both of them are based on the state-based algorithms, which are sound and complete. And there's an if and only if in there, so yes. Both the formula interruptibility checker and the Buki automaton interruptibility checker are sound and complete.
Awesome. Okay. Well, thank you so much. That was a very interesting talk. And actually, speaking of spots, next up we have Alexandre Doralus calling in from Paris, talking about a related tool, Seminator 2, improved semi-determinization and complementation of omega automata.
This presentation is about Seminator 2, a tool that converts generalized Bushy automata into semi-deterministic automata and may optionally complement them. An omega automaton is semi-deterministic if it can be split in two parts. In the left part, you want no accepting cycle and you allow non-deterministic choices. And in the right part, everything has to be deterministic and you can have accepting cycles. You can go from left to right, but not in the other direction. This is sufficient for some applications that traditionally use only deterministic automata, for instance, qualitative model checking of Markov decision processes. And some advantages is that the semi-deterministic omega automata are smaller than their deterministic counterpart. And if you restrict yourself to Bushy acceptance, semi-deterministic Bushy automata are more expressive than deterministic Bushy automata. Our tool, Seminator 2, works not on Bushy automata, but on transition-based generalized Bushy automata. It is built on the Spot library, and in this second version, it has a near complete rewrite of its semi-determinization procedure, and it has an optional complementation algorithm. So if you activate this complementation, the input TGBA is first semi-determinized into a semi-deterministic transition-based Bushy automaton, and then we apply a complementation specific to semi-deterministic automata to obtain a transition-based Bushy automaton. So this algorithm is called NCSB. The new version also has Python binding, which I'm going to demonstrate just now, and some pipe-friendly command line interface. Our Python bindings integrate into those of Spot, so let's first use Spot to translate this LTL formula into this nice TGBA. So a TGBA is an omega automaton, so an infinite run here is accepting if it satisfies this acceptance condition, which says you must see blue infinitely often and you must see pink infinitely often. With generalized Bushy, you can have as many colors as you want. So we can highlight the non-deterministic choices in this automaton, all these transitions. So clearly this loop is accepting and contribute to non-determinism. So this is not a semi-deterministic automaton. To use Seminator, we import the Seminator function from the Seminator plugin of Spot, and we simply call Seminator on this TGBA object, and we get a semi-deterministic automaton. We can pass some argument like highlight equal true to highlight the deterministic part and the non-deterministic part and the non-deterministic choices. We can request a Bushy automaton as output, and for this I need to import BA. So I get a semi-deterministic Bushy automaton this time. Or we can ask for a complement to get a complement Bushy automaton. Let us now compare Seminator 2 against LTL2LDGBA, which is another tool to produce semi-deterministic automata distributed as part of all. As its name implies, it takes an LTL formula as input. So our benchmark will start with an LTL formula, translate it into a TGBA using a Spot translator tool, because Seminator takes only automata as input, and then we run Seminator to get a semi-deterministic TGBA. So we can already do this benchmark on Seminator 1.1 and the new version. And for this benchmark, we have to distinguish on the properties of the input TGBA. If it is semi-deterministic, then Seminator 2 has nothing to do. If it is not semi-deterministic, then Seminator 2 has some work to perform. And we will also distinguish different kind of input formulas. So we have a set of formulas taken from the literature and set of randoms formulas. So to integrate all, we use the LTL2LGBA tools, but this tool has two different configurations, symmetric and asymmetrical. And because we are nice guys, we have decided to take the best of these two configurations for each formula. And we even decided to apply the simplification of Spot, which are already performed inside Seminator 2, to try to improve the automata produced by LTL2LGBA. So you get this table. So in this table, the numbers that are displayed are sum of all states produced by these different tools over all the formula listed here. And because this is a cumulative number, it's biased towards a very large automata that could be produced on a few formulas. So we also display between parentheses the number of cases where one tool produce an automaton that is the smallest of the automata produced by the 4 tool. So you can see on this table that Seminator perform quite well on this metric. And if we draw a scatter plot between these two configurations, you can see that there are dots on both sides of the diagonals. So even though the number of cases below the diagonal is favorable to Seminator 2, it's larger than what all can produce. The only reasonable conclusion we have here is that none of these tools are useless, and both of these tools can be improved. For the complementation, we have more tools to compare. The setup is similar. Start from an LTL formula, translate it into a TGBA, then apply some complementation tools and measure the size of the output TGBA. Two such tools are Spot and Seminator 2. We distinguish 3 cases for the input TGBA. It can be deterministic, semi-deterministic, or not semi-deterministic. In the latter case, Seminator 2 has to semi-determinize it first, and in the 3 cases, it still has to complement it. Other tools use state-based Biushi automata and not transition-based generalized Biushi automata. So for those, we decided to try to simplify the result further using outfit as previous to try to obtain a smaller TGBA if possible. So the resulting table looks like this, and again, these are sums over states produced by these different tools. So we can also count the number of cases where the tools are successful in giving the smallest automaton, and you can see that there are 3 tools that manage to win different categories. So we will now look at the scatter plot for these 3 cases. In this scatter plot, Seminator 2 is on the y-axis, and here you can see the performance against Fribourg plus Spot and the performance against Spot. In both cases, by just counting the number of dots below the diagonal, you can see that Seminator performs slightly better, but there are still many dots on both sides of the diagonal, so the conclusion is similar. None of this complementation algorithm is useless, and all of those can be improved. To finish, you may download Seminator 2 or its experimental evaluation from GitHub, and on Docker Hub you may find a Docker image with Seminator 2, the evaluation, and all third-party tools installed.
Thank you very much, Alexandre. While we're waiting for some additional questions on the Slack channel, I was wondering, do you have this, for example, the sort of demo that you showed also tied into the Spot wiki page? I love demoing, like in my class, for example, how you can just upload, put in the website, and then you can type in formulas and see the automata directly in Spot. There are so many great visualizations on your website. So I was wondering if Seminator 2 is also tied into that.
So can you hear me first?
Yes, I can hear you.
So it's currently not available on the Spot framework, but this is something we could easily add. And currently, everything that has been shown as a demo here is part of the distribution of Seminator. So if you download the Docker image, for instance, you can already run this on any computer with all the complementation tool installed.
Thank you. And thanks for contributing great visualizations with all of this too. It's so helpful.
Right.
We have a question on Slack from Maxi Weininger from TUM. It says, can you give some intuition on what kind of optimizations you applied? Specifically, do you have an idea what is the difference to OWL and when one of the tools will perform better? Can you predict that in some way?
So this is really a question for Fonda. I don't know if Fonda wants to pick up, because he's the guy behind all the implementation of this optimization. Are you here, Fonda?
Yes. Can you hear me?
Yes.
So I would say the main difference between OWL and Seminator is that OWL translates directly the LTL formulas, while Seminator semi-determinizes automata. And the main optimizations that we added on top of what was already in Seminator 1.1 were mainly not doing unnecessary work like don't determinize parts that are already deterministic, and try to use transition-based generalized accepting condition as much as possible.
Okay, and we have one more comment on Slack from Sugaman Bansal, I believe, but Sugaman, your last name's not on here. Thank you for the talk. I'm also an ardent user of Spot. I have two questions for you, both from the point of view of synthesis. Do SDBA have practical benefits in LTL synthesis? And do you believe that semi-deterministic forms of DFANFAs would have such benefits?
I will answer, I don't know for both of these questions. It's unclear to me how you can benefit from this in LTL synthesis. I don't see how, but maybe, I don't know.
All right, well, we'll let you think about that and maybe answer Sugaman's question offline. So thank you very much, Jazz Hands, for a great talk and a very nice demo. I look forward to downloading it myself. Now we're switching back to aerospace themed talks. We had G-Spacer earlier, and now we have RT Lola cleared for takeoff, monitoring autonomous aircraft. And this talk will be presented by Jan Baumeister.
Welcome to my presentation about monitoring an autonomous aircraft with the stream-based specification language RT Lola. This case study is a cooperation between the German Aerospace Center in Brunswick and the CISPA Helmholtz Center in Saarbrücken. We successfully integrated a hardware-based monitor that is built out of the RT Lola framework in the SuperArtist. This unmanned helicopter is used to study new components for autonomous flights as our monitor. RT Lola is a stream-based specification language that monitors the system against a formal specification given as stream equations. The underlying framework currently contains a software interpreter and a compilation to VHDL, which the later one was used in the case study. During the integration, we had three key considerations. First, the monitor needs to deal with the limited resources of a cyber-physical system. This is a crucial difference from a more standard setting such as network monitoring. Then the monitor's integration need to be highly reliable, such that the monitor does not interfere with the normal execution of the system and does not change its behavior. Last, the specification language needs to be expressive enough to formulate the required safety properties. Before I present the monitor's integration, let us first look at the general concept of the RT Lola framework and the used specifications. We formulated the safety requirements in cooperation with the engineers in natural language. Then we transformed the requirements in the stream-based specification language RT Lola. This language was expressive enough to describe the properties, but also has formal guarantees as formal semantics compared to natural language or programming languages. Then we compiled the specification to VHDL and synthesized the code in the next step onto an FPGA. During the flight, the monitor receives the drone's data, analyzes them, and produces a verdict. This output notifies the safety pilot in case of a violation. In our case study, we monitored with these different specifications different parts of the system. The sensor validation is at the lowest level. It monitors the incoming data to check its reliability. Besides the actual value, the specification also analyzes the sensor's timing behavior. For example, if the incoming data frequency matches the frequency required by the system. The second specification, the cross-validation, compares the values of different sensors to recheck the sensor's reliability in another way. For example, if the acceleration measured by the internal measurement unit does not correspond with the current velocity measured by the GPS module, the system receives false data. The last specification is on the mission level of the aircraft. We check if the vehicle stays in the restricted area of the test flight. Otherwise, the aircraft has no longer permission to fly and has to start an emergency landing. As I already mentioned, we used a hardware-based approach for the monitoring process. Using an FPGA, the monitor does not share any computation time with the system, which is the first step to not interfere with the system's normal execution. Another advantage is the parallel computation of the monitor because of the natural behavior of hardware. This decreases the runtime of the monitor, which was shown in the previous work. Additionally, this approach allows the use of different static analyses, for example, to measure the power consumption or the memory consumption of the monitor. With these analyses, we can conclude if the used board is sufficient for the specification and if the aircraft produces enough power to execute the monitor. This determination is done before the flight, which allows a safe integration. In the paper, we presented the result of different static analyses, which some of them are shown in the next slide. First, all 3 synthesized monitors required less than 600 bytes, which is pretty low and fitted on the FPGA. If we look at the power consumption, we can see that the monitors use about 150 milliwatts in the idle state and during a peak about 2 watts. In our setup, the system could spare this power and we could integrate the monitor. In the integration process, we separated 2 levels. The first level is the logical integration. Each component of the system has different requirements depending on their usage, resulting in several specifications. In our case study, we monitored several parts of the system architecture, reaching from the low-level sensor validation to the mission level with the geofence specification. However, when it comes to the actual hardware, the integration of the monitor is for all specifications the same. In our setup, we integrated the monitor and the logging process of the system. This process stores the used sensor data and the computed values of the system for post-flight analyses. We adapted this process to send the data also to the monitor. With this setup, the integration does not interfere with the system's normal operation that was required to guarantee a safe integration. Additionally, because the logger's capacity is not exhausted, the system behavior also does not change with the integration. In preparation for a flight, we set up a simulation environment for the monitor to validate the specifications and their integration. In general, the significant difference between the simulation and the aircraft is the different source of the sensor data, which is taken out of log files instead of an actual sample. With this setup, we can replay recorded flights of the aircraft to test the monitor's integration. Apart from that, the simulation has the same architecture. By using the same computers as the drone, we can simulate the same timing behavior to get an environment that is as close as possible to an actual flight. We validated the specifications with 2 runs. The first one is a regular flight to test the geofence specification. In this graphic, the red line represents the fence and the green line represents the replayed flight. As you can see, we built a fence in a way such that the helicopter produces different violations which the monitor all recognized. The second run was in an enclosed backyard that causes problem for the GPS module. These interferences can be seen, for example, with the presented velocity diagram, which has several high peaks. Because the run has such violations, we could test the monitor compiled from the sensor validation and the cross-validation specification. With these positive results, the next step is now to perform an actual flight to validate the environment and the system impact on the monitor. To conclude, we successfully integrated a hardware-based monitor in an unmanned aircraft system and validated the integration. Additionally, we showed that the used specification language Attila was expressive enough to describe the required properties. Also, the resulting monitors could deal with the limited resources of a cyber-physical system. The static analyses showed that the requirements of the hardware board as well as the aircraft themselves are fulfilled. Because this could be determined statically before the flight, a safe integration was possible. If you have any questions, feel free to ask or visit our website attilula.org.
Thank you so much for a wonderful talk. I love that you guys are doing such real work in RV that can really fly. There's such a rich space there, and it seems like just you guys and our group are working on this, and I would love to see more in this area. As we're waiting for any additional questions on Slack, I had one. I found it really awesome that you highlighted the static analysis beforehand to make sure that you could safely integrate with the aircraft as required for flight certification. That's a really essential thing that we run into all the time too. And a question that I seem to get asked pretty much every time we talk about RV, I always ask this question again just yesterday, is do you have the ability to tune the setup of RT Lola to a specific set of resources. So like, for example, if someone says, okay, I have this FPGA, I have this setup, I have this, some characteristic of the architecture of my aircraft, here is what your resources you're allowed to use, and here are bounds or constraints that you may not go beyond. Can you then start with that and use that to efficiently derive the configuration that you're going to load on the aircraft? Or is it currently more of a sort of like guess and check that you can make a really educated guess and then check it with your static analysis beforehand to make sure that if you integrated it, it wouldn't violate any of those constraints?
Currently, it's more or less just a check to check if this fits on the board, because we use it as a separate component. But in general, because we have the different analysis on the specification language itself to check the memorization parts, for example, how many values we need to store per stream, we can have a guarantee, okay, this is an indication how if this fits on the board or not. So, and for example, in this case study, we used the fence with 12 phases, if I remember right. Then this was more or less the limit. So we tried it with more fences, and this was 14 was the limit with our board. So the next step would be to check if we can have a bigger board with more lookup tables, because most of the time the number of lookup tables was the problem and not the number of flip-flops.
Yeah, that's what we ran into, is we need to be able to sort of take as an input parameter,
Yes.
right? Like each of the resources on our FPGA, and then of course there's more than one way to represent an RV configuration, right? So you can sometimes
Yes.
trade off more of this or less of this, right? And so having that sort of tuning ability is what we get asked about, I think, more than just about anything else. So
yeah, but for the software-based solution, this might not be the problem. So this is the hardware-based solution, but we also have the interpreter and ongoing work for a compiler or software compiler. Then there are other problems maybe, but not the problems with the number of lookup tables anymore. And so maybe this would solve the problem if you go to the software instead of using hardware. But then we have a higher power consumption and so on. So this has also disadvantages.
Right. So there might be other resource constraints in terms of power or something. So yeah, that's always the trade-off. We do the same. All right. So there's a question on Slack, again, from Mir Mohammed Nazari. Expressiveness is one of your factors. How do you prove that RT Lola is expressive enough for all kinds of specifications?
Yeah, we cannot prove it. I mean, if the specification or the properties that were formulated in cooperation with the engineers, and we could formulate them in RT Lola. So yes, sure, there are properties we cannot describe, but at the moment we say that it's expressive enough for most of the time. And if you have any specification we cannot express, then feel free to send them to me, and we try to formulate them in RT Lola. So yeah, we want to push them to the limits and to see what we can express and what we cannot express. So yeah, I hope this answers the question.
I was gonna say we should like join forces and make like a wiki for like, for the actual flight certifiable RV tools, what do you want that we can't do? Because I'm sure your answer would be similar to mine, that while there are some things that people can come up with that we can't express exactly, we can always express some kind of flag or approximator, right? Like, so we can express something that's similar, that's maybe like, some kind of over approximation, so that if you violate this, well, you've certainly violated that. So, and then it just helps with the no false positives anyway. So by the time you factor in that, right, you're very expressive.
But this is the thing, we want to show practical examples if we can express them. And yeah, this is the major point. If you can find practical examples that are really necessary, then not to build theoretical ones. I mean, you can always build them. So this is not the point of our case, and we want to have a practical tool that can be used in industry.
Yes, and you've done an amazing job. I look forward to seeing this carried through and develop more. So thanks for a wonderful talk. Jazz hands. Okay. And for the final talk in our session today, by the same group, also a related talk, we have, and my program just cleared. All right, so we have AtomMC, a model checker for Petri nets that transits against flow LTL. And this will be presented by Manuel Gieseking.
Hello everyone, my name is Manuel Gieseking and I'm going to present our new tool AtomMC. AtomMC is a model checker for distributed systems with specifications on the control part of the system and the local data flow part of the processes. This is joint work with Bernd Finkbeiner, Jesko Hecking-Harbusch and Ernst Rüdiger Olderock. AtomMC takes a model and a specification and answers the question whether the model satisfies the specification or not. So as an example for such a system which separates the control from the data, we consider software-defined networks. And we see here a topology with 5 switches and the corresponding connections. And we take a netcore program to define the initial configuration of the network. So the blue arrows here describe how the data is initially routed through the network. And we would like to update such a configuration. So for example, we would like to obtain the green dashed configuration. And we can compose such an update out of single updates, either with this parallel operator here or with the sequential operator. And the special part here is that we do not restrict our data packages to be either transmitted via the blue, so the old configuration, or via the new configuration. But we also allow any mixture of these configurations. So we do not only check the initial configuration and the final configuration, but also every configuration in between, so during the concurrent update. For specifications, we can say something like we don't want to lose a package or we don't want a package to loop. So this is the first possibility as an input for AtomMC. And in the first step, we take the model here. So we take the topology, the initial configuration, and the concurrent update, and we create a more general model out of this. So we create a Petri net with transits. This is a Petri net with transits, and for the control part, it's really just a standard Petri net. And for the data flow part, we refine the flow relation of the transitions. So for example, here, when this transition fires, all data which is currently then in switch S is then transmitted to switch C. Or whenever this transition fires, new data is given into the network. So for this model, we abstract from the concrete data and focus on the data flow, on the flow of the data. Corresponding to that, we have a specification language, here flow LTL. And we can express our standard properties like drop freedom or loop freedom in flow LTL. For flow LTL, we can use standard LTL to reason about the control part of the system, and we can use standard LTL to reason about the data part of the system. So with this A operator here, we can say all data flows should fulfill the following formula. And we can compose these parts with a conjunction, a disjunction, and an implication. For example, we can say something like, when all transitions in the system are fair, then we would like that all data flows which start in a specific ingress node should eventually reach a specific egress node. So the idea here is that we can select specific runs of the system with LTL, and then can reason about the data of these runs again with LTL. And to answer the question whether Petri net with transits satisfies a flow LTL formula, we reduce this problem to a hardware model checking problem. So we create a circuit and give then this circuit to the hardware model checker ABC. So we have the algorithms for IC3 or bounded model checking at hand to answer the initial question. And this reduction is done in 2 steps. In the first step, we take a Petri net with transits and the flow LTL formula and create a standard Petri net out of this. And here the main idea is that we have one subnet for the control part of the formula, and we have one subnet for each data flow subformula, in which we then track all the data and check whether the formula is satisfied or not. And we have 2 different approaches to combine these nets. On the one hand, there's the sequential approach here, and on the other hand, there's the parallel approach. Corresponding to that, we create also a standard LTL formula out of the flow LTL formula to take care of all these additional steps and the subnets which we saw before. The second part of the reduction is the easier part. So there we create a circuit out of the Petri net, and we have a minor adaptation to the LTL formula. And then we take these two components here and give them to MC Hyper to create the final circuit. For the experimental results, we see here our previous prototype, and what we can see is that we had a lot of timeouts for larger benchmarks. And now with the new algorithm, we can see that we reduced the number of timeouts, and we could also reduce or decrease the amount of time we needed for solving the model checking problem. And this is mainly due to the new parallel approach, which we introduced in this paper. So even though we create, in general, larger nets, we need less temporal operators in the created LTL formula. And this is the main reason for the performance gain here. So to conclude, AdamMC is a new model checker for distributed systems with specifications on the control and the local data flow part. We allow for 3 different kinds of input types. We have, on the one hand, the software-defined networks with the overlapping concurrent updates. We saw the more general model, the Petri net with transits and flow LTL. And we can also solve Petri nets against LTL with places and transitions as atomic propositions. All this is doable in single exponential time with the help of ABC. And our tool is open source and freely available to download. So please feel free to download AdamMC. And thank you.
Thank you for a great talk. While we are waiting for some questions to come up on Slack, I had a couple of questions. So you mentioned that there was the MC, what's that, MC Hyper or something like that tool used, but then also an integration into ABC. So what is the model checker that you are using here? I was a little bit unclear on what do I Google to download your model checker?
To download our model checker, you should first of all download AdamMC, and then you need 2 tools for that. So on the one hand, this is the MC Hyper tool, which is developed in Saarbrücken. And this is for taking a circuit and taking an LTL formula, and then MC Hyper is doing the creation of the Büchi automata and creates a new circuit, and this circuit then can be checked by the ABC model checker. So the hard part, I would say, is done by ABC with all these algorithms which they developed for a long time.
Okay, thank you for clarifying that tool chain. And then I was also wondering, so you mentioned some really interesting possible case studies at the end, like the software-defined networks. And I was wondering, are you using this tool for verification of any of those systems right now? Maybe you could talk a little bit more about the planned applications now that you've released the tool.
Yeah, we started with these software-defined networks and took a look into that. And in future work, we currently try to consider more of access control examples, but then we need branching, and so we extended the logics to CTL and had a and look into this direction. That was the idea, because we the linear part wasn't enough.
Huh. Okay. I wonder if you need full branching or if you just need like kind of one branch to make it to sort of get that effect. I was thinking, I don't know if Ari Gerfinkel is still here, of a paper that he published a few years ago on the logic CSSL, where there was a single CTL branch combined with LTL. And that was a very interesting way of achieving sort of some of the best of both worlds. We have a couple of questions that have come up on Slack, so I will read those to you. So Stefan Siegel asks, is there a reason for using ABC over other model checking engines? I'm assuming like new SMV, things like that.
I mean, our idea was, okay, it's very well developed, and we had, first of all, we had more the idea, okay, maybe we can use a PetriNet model checker for all this, and to not use the last reduction what we did there. And the first thing was that there no transitions were available to reason about transitions in the formulas, and we need that for the fairness. And okay, then there are, for example, the Lola, another Lola tool, which is normally, or in the last years was the winner of the model checking contest in the LTL part. They have kind of fairness, but we had a little bit problems with, so we are in contact with them. And yeah, so that was then the idea, okay, then we have to do a reduction more, and then yeah, the ABC was the first choice because of the well-developed algorithms for a long time.
Ease of integration in the tool.
Yeah.
Okay. So Labna Guda asks, for the data part, knowing the topology of the network between ingress and egress, there might be multiple equivalent paths that share the same properties. Would the trace show a single path?
Okay, so when as a counter example, I understand it right? Yeah, then it would choose one of the paths and would say, yeah, this one is a counter example, and yeah, so it's maybe a little bit non-deterministic which one it's chosen, but yeah.
Sure. Okay, that's as we would expect from lots of model checkers. And then Labna also asks, for the SDN application, was it OpenFlow or was it protocol agnostic?
It is OpenFlow is a very on a very low level, so there are very much details there. So we took a little bit more abstract view on this, and so we took netcore programs. They're called netcore programs to define the initial configuration. So it's more in the direction of OpenFlow, but not that low level. I would say it's more on the high level view of that.
Awesome. Okay, well, thank you very much. Jazz hands, it's been a great session. So thank you to all of the speakers in our session. That was the last talk that we have for you in the model checking session this year. But there is a CAV breakout session, and that is linked on the Smart program on EasyShare. So please feel free to switch over to that link, and then we can continue discussions with our speakers there. Thank you so much, everyone, for coming.